Hello, and welcome to this lesson where we're going to take those Laplace transform techniques and apply them to our circuit elements and a little bit of circuit analysis. Now in this lesson, we're going to take things a little bit slow. We're going to keep it simple. We're just going to look at how do we take the basic circuit elements, the inductor, the resistor, the capacitor, and transform them from time domain into the S domain. And then when we've done that, we'll work a simple example of taking a really simple circuit and converting it from time domain to the S domain. So let's go ahead and get right into it. So transforming a circuit element into the S domain is a three-step process. So we'll say we got 3 steps. Step number 1 is write the time domain expression for the terminal voltage and current. So this is write that V equals IR, V equals, C dVt, that sort of stuff. The expressions for each element. Step 2, apply the Laplace transform. To the expression. And then finally, step 3 is construct a circuit model for the S domain expression. And as you'll see, there's actually a little bit to it. It's kind of interesting. So let's go ahead and do this for each of our 3 basic circuit elements. So let's start with the most simple, the resistor. Now let's go ahead and draw our basic resistor circuit model. So we have a terminal A. We have our schematic symbol for the resistor, and that connects to a terminal B. And the resistor has some value R. There's a voltage drop across the terminals A to B, and there's also a current I flowing through the resistor. So now we already know that Ohm's law is our equation for voltage and current in a resistor. So we know that our V is equal to R times I. And if we take the Laplace transform of both sides of this expression, right, we know that our Laplace transform of V is just, we're going to write a big capital V, and our Laplace transform of I is just a big capital I. Now, the reason we don't take the Laplace transform of R is because R is not a time domain expression. So if I was being a little bit more diligent about this, I would actually say V of t is equal to R times I of t, right? So the Laplace transform only hits the voltage and the current. And we'll see the same thing happen in the inductor and in the resistor. So that means that our expression for, let's do it in red, the Laplace transform of our resistor voltage current expression is exactly what we started with. V equals R times I. And so the model for that doesn't change. It's just our terminal A, our schematic symbol for R, our terminal B. We still have R. There's still a voltage drop of V across the resistor, and there's still a current of I across the resistor, or through the resistor, I should say. So that's the resistor. Like in most of the other things we've looked at, the resistor largely does not care at all about frequency or anything like that. It's always just a resistor. So now let's go ahead and do an inductor. It's a little bit more interesting. The inductor. So just like before, we have our circuit model for a time domain inductor. We've got a terminal A. We've got our inductor schematic symbol, and we have a terminal B. And there's some inductance that we'll denote as L for that inductor. And like before, it has a voltage V across the terminals A and B. It's got a current I that's flowing through it, but there is one other thing that's hanging out, and we'll see that when we take the Laplace transform. There's actually a current I sub naught, so the initial current that's in the inductor when we start the analysis. So this will come back around when we take the Laplace transform. And we know from circuits 1 that our expression for voltage in an inductor is V is equal to L times the change in current with respect to time, di dt. Now, if we take the Laplace transform, we saw this before, but for V, of course, we'll just get capital V. It remains largely unchanged, equals L. The L isn't affected by the Laplace transform, but the Laplace transform of a derivative is going to get us this, S times I minus I naught. Remember, we talked about this in our Laplace transform discussion. The Laplace transform of a derivative subtracts out the initial condition. So if we just distribute the L through the expression, we get this really simple expression for V. V is equal to S Li minus L times I naught. And if we draw that, I'll go ahead and go back to yellow for this. What we'll see is now we have two voltages, right? The voltage drop is now due to two separate elements. So when we go to draw that, we'll say we've got terminal A. We've still got our inductor, but now we actually have a voltage source in series, and then our terminal B. So the impedance of the inductor in our model here is just going to be SL, right? Since it's SL times I gives us the voltage. And the voltage drop here is going to be, first off, in the reverse direction, since it's minus that voltage. If our voltage drop is positive minus from A to B for our big capital V, then the voltage drop for our source here is going to be minus to positive. It's going to be inverted, and that voltage is going to be equal to L times the initial current. And then there's still that new S-domain current flowing through the circuit model. So this is how we transform the inductor. The important thing here is that we get this expression, V is equal to SLI minus Li naught, and we add this voltage source in the expression. Now, if we were concerned with current, we can actually use just a little bit of algebra to transform this expression into an expression for current. So I'll just go ahead and start with that. V equals SLI minus Li naught. If we're going to solve that for I, we're going to get that I is equal to V plus Li naught over SL. And if we distribute out that over SL, we'll get that I is equal to V over SL plus I naught over S, which means we can now write this as a sort of function of current. So we'll have two parallel elements since we have currents. So we have still our node A, but now A is going to branch, and up here we'll draw our inductor, which now has a value 1 over SL. And that goes out to our terminal B. And then down here on this branch, we have a current source. Now notice that it's plus I naught over S. That means that our current is now going to flow in the same direction as our incoming current. And that current is going to be equal to I naught over S. And we still have a voltage drop, V, across those elements, and the current I is coming in from that A node. So we have both versions now, a version for voltage and a version for current. Depending on the analysis that you're doing, one might be preferable to the other. So that's the inductor. Let's wrap things up by taking a look at the capacitor. And basically it's going to be exactly the same conceptually as the inductor. The capacitor. Let's go ahead and write out its time domain, or draw its time domain circuit model. We have node A, we have our capacitor symbol, and we have node B. The capacitor has some capacitance C. It's got a voltage drop across the terminals A to B, plus to minus, and then it has a current I. But just like the inductor had an initial current, the capacitor will have an initial voltage, V naught. So now we go ahead and write out our expression for, this time, current in a capacitor, not in an inductor. That's equal, I is equal to C times the change in voltage with respect to time, C dV dt. So we're going to get an expression that's sort of flipped over from the one that we had before, or the one that we had for the inductor. We'll get that our big S domain, capital I, is equal to C. Now it's S times V minus V naught. And we'll distribute the capacitance into the expression to get that our current I is equal to S times CV minus C times V naught. And notice that we've got an expression for current where we have the sum of two current elements. So we'll do the parallel current source model. We have our node I. We have our first branch that will go ahead and use the capacitor model. And that comes out to node B. We have our source in parallel, also back to node B. Now let's see for our capacitor. Our capacitance here is just SC. And our current source, notice that it's minus that current. So this current source is going to flow in the opposite direction against A, or against the incoming current I, and that's going to be equal to C times V naught. And just like before, we still have our voltage drop across the elements, and we have our current, capital I, coming in from node A. So that's our basic transform. Just like with the inductor, we can convert it to now the voltage of the, or excuse me, an expression of the other element. Before, with the inductor, we went from voltage to current. Here we're going to go from current to voltage, but you can see we're going to get the exact same thing. And we'll get that V is equal to I plus C V naught over SC, which means that we have voltage is equal to I over SC plus V naught over S. So we can draw this expression as just series voltage elements. We have our node A, we have our capacitor, we have our source, and we're out to node B. Notice that it's plus the voltage. That means that our polarity of our voltage source is going to be in line here with the voltage. And the value of that voltage is going to be V naught over S. And the value of the capacitor here is going to be 1 over SC. And we've got our voltage, capital V, between the terminals A and B. And then, of course, we have our current, capital I. So there we go. That is all there is to it for converting, or excuse me, transforming circuit elements, the resistor, the inductor, and the capacitor, from their time domain models into their S domain models. And as you hopefully saw, it's not terribly complicated, but it does involve the inclusion of a new voltage or current source depending on which version of the transform you're doing. Okay, now before we work out an example of doing some circuit analysis in the S domain, let's lay out a few things. The first thing I want to mention is that the S domain impedances are just like the phasors in that everything is sort of an Ohm's law resistor. So we have this S domain, Ohm's law. We'll say that just our capital V is equal to Z times I. So all of our impedances, once we transform them to the S domain, we can sort of treat everything like a normal time domain resistor. Next up, let's go ahead and list out all of the steps required for the Laplace transform. So we'll call this the Laplace transform method. And there are 7 steps. Step 1 is determine the initial conditions for voltage in capacitors and current in inductors. So remember those transforms for those circuit elements involve introducing those new sources. So we're going to need to know what those initial conditions are. So determine V naught for capacitors and I naught for inductors. Step 2, transform any sources from the time domain to the S domain. So if we have voltage and current sources, let's transform those. Transform any sources. Step 3 is transform any symbolic voltages or currents. If our expression, or if the circuit model that we're given already has some voltages or currents defined anywhere in the expression, go ahead and transform those. So we'll say transform any symbolic voltages or currents. That one doesn't happen very often, but there it is. And step 4, transform the circuit elements. So do what we just did, right? Take those resistors, inductors, and capacitors and transform them to their S domain equivalents. Transform circuit elements. Now, step 5 is analyze the S domain circuit. This is the circuits 1 stuff, the mesh current, the node voltage, whatever analysis you're performing, go ahead and do it. And if I can spell analyze though, that'd be pretty cool. Analyze the S domain circuit. So this is do the thing. Next up, 6 and 7 are just sort of optional extras that you can do depending on what your analysis is. First one, step 6, is apply the initial and final value theorems. To make sure everything squares with t, so to check with t equals 0 and t equals infinity. And step 7 is apply the inverse Laplace transform to return the circuit model to the time domain. And I'm going to put in parentheses here if necessary, right? There's not a lot of reasons to convert back. Well, actually, I take that back. When we design our filters, a lot of times we'll design our filters and do our analysis in the S domain, and then we need to actually get the time domain expression so that we can actually build the darn things if necessary. But for what we're doing right now, It's not totally necessary. So there's our 7 steps for the Laplace transform method. I'll just go ahead and recap them for you. Step 1, determine the initial conditions. Determine V naught for capacitors and I naught for inductors. Step 2, if you have any sources, voltage or current sources, transform them. Step 3, if there are any symbolic voltages or currents, this is a weird one. This just means if there's currents or voltages already given to you in your model, go ahead and transform those. Step 4 then is transform the circuit elements. Step 5, analyze the S-domain circuit. This is doing the stuff. This is node voltage, mesh current, whatever it is you're doing for your analysis, do it then. Step 6, apply the initial and final value theorems to check against t equals 0 and t equals infinity. And then finally, step 7, if you need to, apply the inverse Laplace transform to return the circuit model to its time domain equivalent. So there you go. There's our steps for the Laplace transform method. And in the next lesson, you'll see that used a whole bunch. But for now, let's just work out a really simple example. And here we have a parallel RLC circuit. So let's start by drawing. We have a capacitor that is at 25 nanohenries. Excuse me, farads, not nanohenries. I was getting ahead of myself. Then we have an inductor that is at 16 millihenries. Then we have a resistor that is at 500 ohms. And we've got some output terminals. We'll just call them A and B. Now what we want to do is determine the equivalent admittance on the input terminals of this circuit. So we're going to calculate YEQ. But we're going to use our Laplace method techniques here. So the first few steps are pretty easy. Step 1, which you remember was determine the initial voltages for capacitors and initial currents for inductors. Since there are no sources in this circuit, there cannot be any initial conditions. So no V naught or I naught. Or rather, I guess a better way of saying that would be that V naught equals 0 and I naught equals 0 everywhere. Step 2 is check to convert sources. Again, we don't have any sources, so no sources. Step 3 is no voltages or currents, or it's convert any symbolic voltages or currents, of which we have none, so I'll just say none. And then finally, step 4 is converting the circuit elements. This is what we wanted to do. Let's go ahead and jot down our equations that we had before. Remember our voltage and current relationships for our S-domain circuit elements. So we have VR is pretty easy. VR is just equal to let me keep my stuff straight here. R times I sub R for our resistors. Our voltage in an inductor, VL, is equal to S Li minus Li naught. And our VC is equal to I over SC plus V naught over S. Now remember, both of our initial conditions here are 0, so those elements, we'll lose them and they'll go straight to 0. And we'll keep our impedances for the inductor and for the capacitor. So let's transfer back to white. That means our impedance, ZR, is still just equal to 500 ohms. Our impedance ZL is equal to S times L, which is 16 times 10 to the negative third, also ohms. And ZC is equal to 1 over SC, which is going to be 1 over S times 25 times 10 to the negative 9 ohms. And I want to get that value out of the denominator, so I'm going to do 1 over 25 times 10 to the negative 9 is going to give me 40 times 10 to the 6 over S ohms. So there are my transforms for the resistor, inductor, and capacitor. So next up, let's go ahead and build the circuit model for that. Let's use a different color. So our capacitor has an impedance 40 times 10 to the 6 over S ohms. Our inductor has S times 16 times 10 to the negative 3 ohms times S. Our resistor has 500 ohms. And they're all connected in parallel. We still got our terminals A and B, A, B, and we're still hunting for that Y EQ across the terminals. Now, one of the reasons I think this example asks us to do admittance is because it's pretty easy to do admittances in parallel. In fact, it's easier to do that and then flip them over to series. Let's recall our equation here before we give it some values. Our Y EQ is just going to be equal to the sum of the admittances, which is 1 over the impedances. So that'll be 1 over ZR plus 1 over ZL plus 1 over ZC. So let's go ahead and apply some values to that. We'll get that Y EQ is equal to 1 over 500 plus 1 over S times 16 times 10 to the negative 3rd plus, now it was Z of C was 40 times 10 to the 6 over S, so it's going to flip over and we're going to have S over 40 times 10 to the 6. And all of that is given in the unit of admittance, which is Siemens. And now we can go ahead and simplify this expression. And let's go ahead and work it out. Just for kicks and giggles, we'll say that, remember how we combine stuff with different denominators? That means that we're going to have, what, S times 16 times 10 to the negative 3rd times 40 times 10 to the 6 plus 500 times S times 16, what am I writing? S times 16 times 10 to the negative 3rd plus 500 times, I messed that one all up. Let's see. I got ahead of myself. The middle one should be S times 40 times 10 to the 6 plus S times, now this one is 500 times S times 16 times 10 to the negative 3. So make sure I got that right. So that's, first one is this denominator over this denominator. S times 16 times 10 to the negative 3rd times 40 times 10 to the 6 plus the middle one should be 500 times 40 times 10 to the 6 plus this one should be S times the other two denominators, 500 times S times 16 to the negative 3rd. And that whole expression will be over the product of everything. So that's 500 times S times 16 to the negative 3rd times 40 times 10 to the 6. Now, if you go ahead and punch those values in your calculator, you'll get, and I'll kind of rearrange it to make it a quadratic, that gets us 8S squared plus S times 640 times 10 to the 3rd plus 20 times 10 to the 9 over S times 320 times 10 to the 6. Now, one last step before I call it done. We don't want to leave, we want to make everything a nice, pretty quadratic equation. So I'm going to factor the 8 out of the S squared. And that'll give me, well, first S squared plus 640 times 10 to the 3rd divided by 8 is 80 times 10 to the 3rd, and that's times S, plus 20 times 10 to the 9 divided by 8 is 2.5 times 10 to the 9 over, Now 320 times 10 to the 6 divided by 8 is 40 times 10 to the 6. So we're going to have S times 40 times 10 to the 6. And that's given in Siemens. So there is our solution for equivalent admittance in the S domain. Now, all of that was super fun, but the reason we would even care to do it in the first place is because for this circuit, we want to do what we're asked to do here in part B, which is calculate the poles and zeros for YEQ. This will come back in a big way in another chapter. Okay, so for the poles, it's pretty easy. We look down in the denominator. We just have S times 40 times 10 to the 6. There's no math required there. We just know that we have a pole at S equals 0. Now for the zeros, we need to go ahead and solve that quadratic equation. And like before, I'm going to choose to be lazy and just use Wolfram alpha. And write solve S squared plus S times 80 times 10 to the third plus 2.5 times 10 to the 9. And we're going to solve that for S. And we will get, there we go, minus 40,000 minus 30i and minus 40,000 plus 30i. So we will go back and drop that into our zeros. So we have zeros at S equals minus 40,000 plus J 30,000 and S equals minus 40,000 minus J 30,000. And there we go. So in this lesson, we took a look at just the basics of how to transform our fundamental circuit elements into the S domain. We looked at resistors, inductors, capacitors. The big take home there is don't forget that you got to look out for those initial conditions, the V naught in the capacitor and the I naught in the inductor. We also worked a really simple example of just converting a parallel RLC circuit to the S domain and then calculating its equivalent admittance and also using that to calculate the poles and zeros for that circuit. In the next lesson, all we're going to do is work a bunch of examples of applying those circuit 1 techniques, node voltage, mesh current, Thevenin and Norton equivalent circuits, all of those basic circuit 1 techniques. We're going to then work some examples of applying those in the S domain. So as always, if you have any questions, comments, or concerns, please let me know. And if not, I look forward to seeing you guys in the next lesson. Thank you.